This is Pat Dugas. This screencast is on solving quadratic equations analytically using the quadratic formula and the discriminant to help us. So let's take a look at the quadratic formula itself. We can find the solutions of any quadratic formula in our standard form of ax squared plus bx plus c equals 0, as long as a isn't 0, which would make it non-quadratic anyway, by the formula x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Super important formula to know, because this will crack open any quadratic. And so the a, b, and c terms that are in this quadratic formula refer to the a, b, and c coefficients in each of the quadratic terms. So for example, with x squared plus 5x plus 6 equals 0, the a is equal to 1, the b is 5, and the c is 6. And so we're going to take that 1, 5, and 6, plug them in for a, b, and c respectively throughout the quadratic formula, and it gives us our solution. So this is negative b, which is negative 5, plus or minus the square root of b squared, 5 squared, minus 4 times a, which is 1, times c, which is 6, all over 2 times 1. So how does it get the way it is? So we know that every quadratic is divided symmetrically into two parts by the axis of symmetry, which has the equation x equals negative b over 2a. Well, that happens to be the first part of the quadratic formula. So the center is along x equals negative b over 2a. That's where the negative b over 2a comes from. And then we move from that center line a distance of square root of b squared minus 4ac over 2a and negative square root of b squared minus 4ac over 2a. That's where the plus or minus b square root of b squared minus 4ac over 2a actually comes from. That's the distance from the axis of symmetry. And that's where our solutions occur. Whether there are two of them, one of them, none of them, that's how it works. Let's look at an example. Let's solve x squared minus 8x equals 33 using the quadratic formula. Now, truthfully, this one could be solved through factoring faster, probably, but we're going to use the quadratic formula because it always works. So we're going to write the equation in terms of ax squared plus bx plus c equals 0 in our standard form, and then identify the a, b, and c. So x squared minus 8x equals 33. We're going to subtract 33 and bring it over to the other side through the subtraction property of equality. That leads to 1x squared minus 8x minus 33 equals 0. So the next thing we're going to do is identify the a, b, and c. Well, the a is the coefficient on the x squared term, that's 1. The b is negative 8, coefficient on the x term, and the c is negative 33. Got to identify those next. So then we're going to take that a equals 1, b equals negative 8, and c equals negative 33 and substitute them into the quadratic formula. You really need to commit this to memory if you're going to use the quadratic formula to solve quadratic equations. So when we substitute a negative 8 for b, we get negative b, which is negative of negative 8, plus or minus the square root of b squared, which is negative 8 quantity squared, minus 4 times 1, a is 1, times c, which is negative 33, all over 2 times a, which is 2 times 1. A lot of algebra needs to take place now, a lot of order of operations. Be very careful. Common mistakes are not to turn this into a positive. When anything is squared in the real number system, it becomes positive. So that first part of this radical is going to always be positive. So that becomes negative 8, positive 8, plus or minus the square root of 64 plus 132. When we multiply negative 4 times 1 times negative 33, we get 132, all over 2. So we get 8 plus or minus the square root of 196, all over 2. It becomes 8 plus 14 over 2, or 8 minus 14 over 2, which yields our two solutions, x is 11, or x equals negative 3, both of which are solutions to the equation. Let's do an example that winds up with irrational roots, and we'll see why in a second. So x squared minus 6x plus 2 equals 0 using the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But we're going to identify the a term. So we know a equals 1 because that's on the x squared. B in this case equals negative 6. And c equals 2. So we're going to use that information, plug that into the quadratic formula, and solve. So we get the negative of b, which is negative 6, plus or minus the square root of b squared, negative 6 squared, minus 4 times 1 times 2, all over 2 times 1. When we simplify that, we get the negative of negative 6, which is positive 6. Our negative 6 squared, which is 36, minus 4 times 1 times 2, minus 8, becomes positive 28, all over 2. We're going to simplify that. But because the square root of 28 is not a perfect square, this is going to wind up being an irrational couple of numbers here. So in simplest radical form, square root of 28 is 2 times the square root of 7. So we get 6 plus the 2 times square root of 7 over 2, or 6 minus 2 times the square root of 7 over 2. Okay, so we're going to take it one more step, and we get x equals 3, which is 6 divided by 2, plus 2 square root of 7 over 2 is equal to just the square root of 7, or x equals 6 over 2, which is 3, minus 2 square roots of 7 over 2, which is minus the square root of 7. Those are exact answers. If we needed to use a decimal equivalent, we could do that as well and round it to the appropriate number of decimal places. Let's look at an example where we wind up with complex roots because there are no real solutions. You'll recall that complex roots occur when there are actually no real solutions, no real intercepts on the x-axis. So x squared plus 13 equals 6x. We're going to move the 6x to the other side through subtraction, which gives us x squared minus 6x plus 13. And so our a term is 1, our b is negative 6, and our c is 13. So we're going to replace the a with 1, the b with negative 6, and the c with 13. So we have negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 13 all over 2 times 1. So that gives us, because inside this radical we get negative 6 squared is 36, minus 4 times 1 times 13 is 52. We get 36 minus 52, or negative 16. So 6 plus or minus the square root of negative 16 over 2. When we simplify that, you'll recall that we have to use complex numbers because the square root of negative 16 is going to be 4i. Because the square root of 16 is the square root of negative 1 times the square root of positive 16, which is I times 4, or better written 4 times I. So our two solutions are 6 plus or minus 4i over 2. And that becomes 3, 6 divided by 2, plus 4i over 2 is equal to 2i. So 3 plus or minus 2i. So it's either 3 plus 2i or 3 minus 2i. Those are our two solutions in complex form. When you do enough of these, you see a pattern that occurs. And the key to that pattern is what's called the discriminant, which is the part inside the radical. And that's b squared minus 4ac. That part inside the radical determines the nature of the roots. If that number is positive inside that radical, that square root of b squared minus 4ac, if it's positive, we are going to have two real roots. That's these first two cases here. We're going to intercept the x-axis twice if that's positive, because it's going to be plus or minus that radical part. The only difference becomes if it becomes a perfect square. If b squared minus 4ac is a perfect square, the roots are also rational. In other words, we're going to hit at a rational number, a number that can be written as a ratio. If it's not a perfect square, which happens most of the time, it winds up being an irrational number. Nevertheless, both of these cases are real. There is a somewhat rare case where b squared minus 4ac is equal to 0. In that case, we have one real rational root because we've intercepted the x-axis in one place. And the final situation occurs when b squared minus 4ac inside the radical, the discriminant, is less than 0. If that's true, then there are two complex roots because the function never touches the x-axis. And it looks something along the lines of this. The function does not intercept the x-axis. So let's look at a few examples of how we would use the discriminant. So if we have x squared minus 11x plus 10, the a is 1, the b is a negative 11, the c is 10. If we plug that into the discriminant, b squared minus 4ac, we get negative 11 quantity squared minus 4 times 1 times 10, which is positive 81. Since 81's a positive number and is a perfect square, we have two real and rational roots. In the case of x squared plus 3x plus 5 equals 0, a is 1, b is 3, c is 5. We plug it into the discriminant, we get negative 11. That means we're going to have two complex roots, and it's never going to touch the x-axis. In the case of x squared minus 6x plus 9, a is 1, b is negative 6, c is 9. The discriminant, b squared minus 4ac, is equal to 0. And that's that case where it intercepts the x-axis at the vertex. So we have one real rational root. In the case of 2x squared plus 5x minus 8 equals 0, a is 2, b is 5, c is negative 8. We get positive 89. It's a positive number, but it's not a perfect square. We have two real irrational roots, and those are the four possibilities with the discriminant. This screencast involved using the quadratic formula to solve any quadratic equation and the discriminant, b squared minus 4ac, to help tell us what is going on with the roots and what type they are.